Imagine you're cruising down the highway,
Hmm.
right? It's a perfect afternoon, the sky is totally clear, and the road is just wide open.
Sounds pretty ideal.
Yeah, exactly. You're doing a really comfortable 70 miles per hour
Yeah.
in this state-of-the-art electric vehicle. There's no engine noise,
Hmm.
no vibration. It's just that smooth, effortless glide.
The EV experience.
Right. It feels incredibly peaceful. But what you don't see, like what is completely hidden from you as the driver, is that right beneath your seat, there's this invisible, microscopic war being waged every single second you're driving.
Yeah, it really is a war zone down there. I mean, inside that heavily armored, sealed vault of the high-voltage battery pack, it is a remarkably violent environment.
Which is wild to think about because it feels so quiet in the cabin.
Oh, totally. But we're talking about extreme thermal shifts, high-frequency physical vibrations, rattling components thousands of times a minute, and just, a continuous bombardment of massive electromagnetic noise.
An engineering nightmare.
It really is an engineering nightmare.
And so our mission for this deep dive today is to explore exactly what happens when that war claims a casualty. We are looking deep into the hidden nervous system of your EV.
Specifically, the communication networks inside the high-voltage battery management system, or the BMS.
Right. And we are going to examine a scenario that the engineering documents we have for today call the data blind spot.
Which sounds ominous.
It really does. We want to know, what happens if a microscopic solder joint, something literally no bigger than a single grain of sand, just snaps because of all that vibration?
Right. Does the car's main computer suddenly go completely blind to the battery's health?
Exactly. Will the car just stop dead in the middle of the highway? Will you crash?
Well, I mean, the idea of losing the connection to a massive energy source propelling a 2-ton vehicle at highway speeds, that is terrifying.
Completely terrifying.
If that communication drops, the car is essentially flying blind. But what we're going to unpack today is the almost unbelievable level of modern automotive engineering designed to prevent that exact catastrophic failure.
It's honestly mind-blowing how the car saves itself. But, before we get into the cure, I want to make sure we have a really clear picture of what this system actually looks like.
Good idea.
I like to think of a EV's battery pack like a human body. So the thousands of individual battery cells packed in there, those are the muscles, right?
Yeah, they do the heavy lifting. They store all the kinetic energy.
Exactly. And the battery management system, the BMS, that is the brain. It's making all the strategic decisions about charging, discharging, cooling, all that stuff.
But connecting those muscles to that brain requires a nervous system, a digital spinal cord, basically.
Right. And how does that spinal cord actually work?
Well, it's a highly accurate way to visualize it. And in this case, that digital spinal cord is made up of 2 distinct networks.
Okay, 2 networks.
Yeah. You have the internal daisy chains communicating deep inside the battery pack, and then you have the external CAN bus.
And the CAN bus is what talks to the rest of the car.
Exactly. It communicates with the vehicle controllers, and just like the human nervous system, if you sever that spinal cord, the brain can no longer tell the muscles what to do.
And even worse, the muscles can't warn the brain if they're overheating or taking on damage.
Precisely. So we need to understand how this digital spinal cord functions, how it physically breaks down in the real world, and most remarkably, how it manages to digitally heal itself.
Before the driver even notices a single warning light on the dashboard, which is just the craziest part to me. You usually wouldn't even feel a hiccup in your drive.
You really wouldn't.
But let's start at the beginning. How does a seemingly solid, multi-million-dollar piece of machinery actually break down at the microscopic level? What causes the disease?
To understand the breakdown, we really have to look at what mechanics and engineers see when a car does fail. They plug in their diagnostic tools, and they look for very specific fault codes.
And our source material focuses heavily on a few critical ones, right?
Yeah. Specifically, U0100 and U0111, which indicate a total collapse of the external communication network.
The CAN bus.
Exactly. And then there's U029A, which points to a localized internal communication failure deep inside the battery pack.
Okay, let's isolate that internal failure first, the U029A code. What exactly is failing deep inside the pack there?
So this specific code flags a failure in what engineers call the internal CSC daisy chain.
CSC.
It stands for Cell Supervisory Circuit. Imagine a massive EV battery pack. It's not just, one big battery. It is made up of hundreds, sometimes thousands of individual cells.
Right, like a bunch of AA batteries back together.
Yeah, essentially. And it's physically impossible for one main computer to monitor every single cell directly. So engineers use these CSEs as localized slave boards.
They just sit right on top of the cell.
They sit right on top of groups of cells, yeah, constantly taking their temperature, checking their voltage, making sure everything is balanced.
Like middle managers reporting to the CEO.
That is exactly it. And these middle managers are linked together by a physical wire, passing the reports down the line from one board to the next until the final report reaches the master board.
And that's the daisy chain.
That's the daisy chain. But the problem is, the environment these boards live in is absolutely brutal.
Because they're sitting right on top of those chemical cells, and those cells get hot.
Oh, they get incredibly hot very quickly. I mean, think about when you plug into an ultra-fast charger on a road trip. You are pumping hundreds of amps of current into those cells. The temperature spikes aggressively.
Right.
Or even when you accelerate hard to merge onto the freeway, the cells rapidly discharge, generating massive heat again.
And then what if you park the car overnight in the winter?
Exactly. The temperature plummets to freezing. So these tiny circuit boards are constantly being baked and then frozen over and over again.
So how does that temperature swing actually cause communication failure?
Well, it comes down to a physics concept called CTE mismatch.
CTE mismatch, what is that?
CTE stands for coefficient of thermal expansion.
Okay.
Every material in the universe expands when it gets hot and shrinks when it gets cold, right? But they all do it at entirely different rates.
Oh, I see. So if you have different materials bolted or glued together, they're basically going to fight each other when the temperature changes.
That is the exact mechanism of the failure. These tiny circuit boards are made of fiberglass and resin.
Right.
But soldered onto them are microscopic components, things like filter inductors, common mode chokes, isolation capacitors, and these are often made of dense ceramics or heavy metals.
So they don't expand at the same rate?
Not at all. The fiberglass board expands at a different rate than the rigid ceramic component sitting on top of it.
And the only thing holding them together is that tiny bead of metallic solder.
Exactly.
And it must be like a microscopic tug of war every single time you charge the car.
It is a violent tug of war. And over thousands of miles and hundreds of charging cycles, this repeated thermal cycling induces severe mechanical fatigue in that tiny joint.
So it just breaks.
Yeah, micro cracks begin to form inside the solder. They start small, completely invisible to the naked eye, but eventually they propagate all the way through the joint.
And the engineers call this a cold solder open circuit, right?
Yes. The physical bridge holding the wire to the board literally snaps. The data just hits a literal dead end.
Wow. Okay, so that explains the temperature side of the war zone. But our sources also mention something called fretting.
Fretting.
Which, I mean, it sounds like a mild annoyance, like worrying about something. But in electrical engineering, it sounds devastating.
Fretting is one of those hidden killers in automotive design. While thermal expansion attacks the solder joints on the boards, fretting attacks the physical plastic connectors where the wire harnesses plug into those boards.
Actual plugs.
Yeah, the low-voltage pins. Even though they are snapped into place with plastic locks, they are never truly motionless.
Well, yeah, because the car is always moving. You hit a pothole, you drive over a washboard dirt road, the whole chassis vibrates.
And those macro vibrations from the road translate into microscopic vibrations at the connector. The metal tin wiggles inside its socket on a micrometer scale.
Like, how small are we talking?
We are talking about movements smaller than the width of a human hair. But it is happening hundreds of times a second.
And just that tiny bit of rubbing is enough to break the connection.
Well, it doesn't break the connection physically at first. It destroys it chemically.
Chemically? How?
Most of these low-voltage pins are plated with a thin layer of protective metal, like tin. As the pin rubs back and forth, this micro-fretting, it scrapes off the microscopic layer of oxidation that naturally forms on the tin.
Okay, so it rubs the protection off.
Right. And that exposes fresh, bare metal to the air, which instantly oxidizes again. Then it rubs back, scraping off the new layer, exposing fresh metal again.
So it's like it's constantly sanding itself down and rusting over and over.
Exactly. This process is called microarc oxidation. And over time, all that scraped off oxidation builds up inside the microscopic gaps of the connector.
And rust isn't a good conductor, is it?
No, oxidation is an insulator. It does not conduct electricity well at all. Suddenly, the electrical resistance of that connection starts to skyrocket. The delicate, low-voltage data signals just can't push through that layer of built-up rust.
So the signal degrades until it's dead. But the sources also mentioned a physical failure here, too. something called terminal pushout.
Yeah, that's the mechanical side of the vibration. If the vibration hits the resonant frequency of that specific connector, the mechanical lock inside the plastic housing can just fatigue and fail.
So it unplugs itself.
The pin literally wiggles itself backward until it unplugs itself from the socket. The wire is still inside the plastic plug, so it looks fine from the outside, but the metal contact has completely backed away.
Wow. A total loss of communication.
What a loss.
Okay, so we have thermal expansion tearing solder joints apart and high-frequency vibrations literally rusting or vibrating pins right out of their sockets. But there is a third root cause mentioned for these internal U029A failures, and this one involves the electricity itself.
Right, EOS.
Electrical overstress. How does the car's own power system break its communication lines?
To understand EOS, we really have to look at the architecture. The internal daisy chains are low-voltage networks. They operate on tiny fractions of an amp using very delicate 3-volt or 5-volt logic signals to talk to each other.
Okay, standard computer stuff.
Exactly. But they are physically located inside a battery pack that contains 400 or sometimes even 800 volts of raw, highly destructive DC power.
So they're living next door to a volcano.
Precisely. To protect the delicate low-voltage chips from those high-voltage battery cells, engineers use microscopic isolation barriers, usually things like isolation transformers or specialized capacitors.
Okay, what do those do?
Think of them as incredibly strong, invisible electrical floodgates. They allow the low-voltage data to pass through magnetically, but they physically block the high-voltage electricity from crossing over.
But I'm guessing those floodgates can break.
Under normal conditions, they are perfect. But during ultra-fast DC charging, or, the exact moment the massive high-voltage relays slam shut to connect the battery to the electric motors, you don't get a smooth flow of power.
It's a spike.
You get massive transient surges, spikes of high voltage that just bounce through the system. And if those surges exceed the physical limits of the isolation material, the electricity literally burns a microscopic hole right through the barrier.
It just punches through.
It punches through the floodgate and instantly vaporizes the delicate communication chip on the other side.
That is just catastrophic.
It is.
And all of that, the thermal cracking, the fretting, the electrical surges, that only covers the internal network inside the battery pack.
Right, that's just the inside.
Because our documentation highlights that the external network, the one generating those U0100 and U0111 fault codes, faces an entirely different and frankly much weirder set of enemies. We are talking about the CN bus now.
The controller area network, or CAN bus. It's essentially the central nervous system of the entire vehicle. It is the main internet highway where the battery talks to the electric motors, the braking system, the dashboard, the steering, everything.
It's carrying the most critical safety data in the car.
Absolutely.
And according to the engineering analysis, the biggest threat to this vital network isn't necessarily a wire breaking, it's noise.
Yes.
Specifically, common mode electromagnetic interference, or EMI. But where is this noise coming from? I mean, it's an electric car. It's supposed to be quiet.
Well, it is acoustically quiet, sure, but electromagnetically it is screaming.
Screaming.
The primary culprit is the traction motor's inverter. See, the battery provides direct current, DC, but the electric motors that drive the wheels run on alternating current, AC.
Okay, so you need a converter.
Right. The inverter sits right between them, taking the steady DC power and violently chopping it up to simulate an AC wave.
And when you say chopping it up, how fast are we talking?
Thousands, sometimes tens of thousands of times per second. Modern inverters use advanced semiconductor switches, typically IGBT's insulated gate bipolar transistors, or increasingly silicon carbide components.
And they just turn on and off.
These switches are turning massive amounts of power, like hundreds of amps at hundreds of volts, on and off with just incredible speed.
And every time you slam a massive electrical switch, open or closed, it creates a disturbance, doesn't it?
A huge disturbance. In physics, we look at the rate of voltage change over time, which is known as dV/dt. Because these silicon carbide switches turn on and off so incredibly fast, the dV/dt is massive.
So what does that actually do?
Every single switch event creates a violent electromagnetic shock wave that just radiates outward from the inverter.
So it's basically a radio jammer sitting right next to the battery.
That is exactly how it acts. And the CN bus network is made of copper wires, right? Copper wires act as perfect antenna. So these wires just soak up all this high-frequency noise radiating from the inverter. Now, the CAN bus tries to communicate using tiny voltage differences between two wires. It's what we call differential logic.
So how does differential logic work?
It sends a message by making one wire slightly higher in voltage and the other slightly lower. It's a very delicate balance.
But if a massive electromagnetic shock wave washes over both wires at the exact same time,
It drowns out the signal. The tiny voltage difference is completely buried under a massive spike of random electrical noise. The computer at the other end is listening for this delicate whisper, and suddenly a jet engine just roars right next to its ear.
the ones and zeros just become complete garbage data.
Utter garbage.
That makes perfect sense. But there is another vulnerability on this external CAN bus that honestly sounds kind of absurd when you first read it in the document.
The terminal resistors.
Yes. Our sources talk about this terminal resistor issue. They claim that if a tiny, inexpensive resistor falls off the end of this network, the entire car's communication system can completely collapse. How does one missing piece of cheap electronics take down a whole vehicle?
This actually takes us into a really fascinating area of physics called transmission line theory. To understand it, we have to look at the geometry of the network. A CAN bus is basically a long linear pair of wires running through the car, with various computers tapped into it along the way.
Okay, pretty straightforward.
But electricity doesn't just flow through a wire instantly like water through a pipe. It travels as an electromagnetic wave.
Okay, so a computer sends a message and a wave of electricity shoots down the copper wire.
Right. And at each physical end of that long main wire, engineers place a tiny 120 ohm terminal resistor. Now, these resistors are not there to restrict current like a normal resistor in a basic circuit.
What are they doing then?
They are there to match the characteristic impedance of the copper wire itself.
Characteristic impedance. That sounds heavy. Can we visualize this somehow?
Sure. Think about a long, narrow swimming pool.
Okay, I have a pool.
If you stand at one end of that pool and shove a paddle back and forth in the water, you create waves that travel down the length of the pool, right? That's your computer sending data pulses down the wire.
Okay, I have my paddle. I'm sending waves. What happens when the waves hit the other end of the pool?
Well, if the other end of the pool is just a hard, flat, concrete wall, the wave is going to crash into that wall and bounce violently backward. It reflects.
Right.
And as that reflected wave travels back toward you, it collides with the new waves you are still trying to create with your paddle. The pool just becomes a chaotic, choppy mess. You can no longer tell what the original wave looked like.
That makes a lot of sense. The bouncing wave destroys the new data. So what do the terminal resistors do in this analogy?
The 120 ohm terminal resistors act like a soft, sloping, sandy beach at the end of the pool. When the wave of water hits the beach, the sand absorbs the energy smoothly. The water washes up, dissipates, and absolutely nothing bounces back. The water in the pool stays perfectly calm, allowing your new waves to travel cleanly.
Oh, that's brilliant. So when a computer sends a high-speed digital pulse down the CAN bus wire, it hits that 120 ohm resistor at the end, and the resistor entirely absorbs the electrical energy, converting it into a tiny bit of heat.
Exactly. No electrical reflection.
And the sources say there's a resistor at both ends.
Right. And because there is a 120 ohm resistor at both ends of the wire, wired in parallel, the total resistance of the entire network is perfectly balanced at 60 ohms. This 60 ohm environment allows the high-speed data to flow flawlessly.
But, and this goes back to what we established earlier, this car is vibrating violently on the road.
Yes, it is.
What if the thermal cracking or the fretting causes one of those terminal resistors to literally just snap off the circuit board?
Well, the sandy beach instantly disappears, and you are left with a hard concrete wall.
So the wave bounces.
Instantly. The impedance of the network jumps immediately from a balanced 60 ohms back to a restrictive 120 ohms. When the next data packet flies down the wire and hits that broken end, the impedance mismatch causes the energy to bounce directly back up the wire.
It creates an electrical reflection.
Engineers call it a standing wave. This reflected voltage collides with the incoming data packets at near the speed of light. The physical waveform of the data is distorted so badly that a clean, square, digital one looks like a jagged, messy spike, and a zero looks like random static.
So the receiving computer is just seeing gibberish at that point.
Utter gibberish, and the CAN bus protocol is actually designed to be highly secure. Every time a computer receives a message it can't understand, it increments an internal error counter.
Okay, it keeps track of the mistakes.
Exactly, and because the standing wave destroys almost every single message, that error counter skyrockets instantly.
The analysis mentions that the counter hits 255. What is the significance of that specific number?
In the 8-bit logic of the CAN controller, 255 is the absolute maximum limit. It literally can't count higher. Once a node on the network hits 255 errors in a fraction of a second, the software assumes that it is fatally compromised or perhaps maliciously attacked.
So what does it do?
To prevent itself from accidentally acting on corrupted data like, accelerating when it shouldn't, it triggers a state called bus off.
It just cuts itself off from the network.
It completely shuts down its own communication transceiver. It goes silent to protect the rest of the car. But if the battery management system goes bus off, the rest of the car loses its connection to the battery. And boom, you have the U0100 failure.
Wow. And beyond the noise and the resistors, the final vulnerability mentioned in the root cause analysis is power network collapse. Things like a 12-volt brownout or a DC-DC load dump.
This is a really critical point. While the high-voltage battery drives the wheels, the brains of the car, the computers, the screens, the sensors, and the communication transceivers, they all run on a standard 12-volt low-voltage system, just like an old gas car.
Right, there's usually a small 12-volt battery hidden under the hood somewhere.
Exactly. And if something causes that 12-volt system to falter, say, a heavy electrical load kicks on and the voltage drops below 4.5 volts for just a few milliseconds, that is a brownout. The silicon microchips powering the CAN transceivers simply don't have enough electrical pressure to function. They lock up.
And the opposite. A load dump. What's that?
A load dump is a massive surge on the 12-volt line. In an EV, the 12-volt battery is continuously recharged by a DC-DC converter that's pulling from the high-voltage pack.
Okay.
If a connection suddenly breaks while it's charging, all that energy has nowhere to go. And the 12-volt line can suddenly spike above 16 volts, sometimes hitting 40 or 50 volts for a fraction of a second.
What does that do to the chips?
This massive overvoltage crashes right into the silicon. It permanently destroys the microscopic PN junctions, which are the fundamental building blocks of the silicon inside the transceivers.
Okay, I need to pause here because looking at this list of vulnerabilities is honestly alarming.
It's a lot.
It's a ton. We have thermal tug-of-wars cracking microscopic solder joints. We have low-voltage pins vibrating until they literally rust themselves into insulators. We have high-voltage surges punching holes through isolation floodgates. We have motor inverters screaming electromagnetic noise like jet engines. And we have tiny terminal resistors snapping off and turning the communication lines into chaotic, wave-reflecting swimming pools.
You got the picture.
I have to ask, as a consumer, if I am spending upwards of $80,000 on a cutting-edge electric vehicle, how is it acceptable that a single tiny metal pin wiggling loose over a pothole can blind the main computer? It sounds incredibly fragile.
Your reaction is completely valid, and it's exactly why automotive engineering is one of the most difficult disciplines in the world. You're basically asking for a supercomputer to operate flawlessly while being strapped to a vibrating, heating, freezing chassis hurtling down a highway for a decade.
Which, when you put it like that, sounds impossible.
The truth is, physical parts are subject to the laws of entropy. In a brutal environment, physical things will break. You cannot build a wire that will never, ever snap under infinite stress.
So if the engineers know they can't make the hardware perfectly unbreakable, what is the solution? Just hope for the best.
No, the solution is a fundamental shift in design philosophy. Modern automotive safety is not about ensuring a wire never breaks. It is about designing a system so intelligent, so adaptable, that when the physical wire inevitably snaps, the software architecture instantly outsmarts the hardware failure.
And that pivot leads us directly into the second major phase of our exploration today: technical architecture and self-healing. This is where the car fights back. If the physical wiring is the spinal cord, we are now looking at the vehicle's digital immune system.
Precisely. We need to look at how the software responds in the milliseconds after a physical break occurs. And the most elegant example of this in the source material is the strategy used for those internal battery slave boards, the CSEs we talked about.
Right.
The system relies on a concept called bidirectional ring topology.
This is one of the most fascinating engineering solutions I've seen in these documents. Let's break down exactly how this topology works. You mentioned earlier that the slave boards monitor the battery cells and pass the data down the line to the master board, like a daisy chain.
Right. Normally, a daisy chain is just a straight line. Board A talks to board B, which talks to board C, and so on, until the final board talks to the master.
Makes sense.
The problem with a straight line is that if the wire breaks between board B and board C, every board after the break is completely cut off. The data cannot jump the gap. That creates your data blind spot.
But a bidirectional ring topology changes the geometry of the network, right?
It does. Instead of a straight line, the final slave board in the chain is wired all the way back to a second separate port on the master board. It creates a complete circle, a closed loop.
Okay, let's visualize this. Imagine a mail delivery route on a circular road around a lake. The post office is the master board. The mail truck leaves the post office, drives down the right side of the lake, stopping at each house, which are the slave boards, dropping off instructions and picking up battery data. It travels the full circle until it arrives right back at the post office from the left side.
In a healthy system, that is incredibly efficient. The data flows in one continuous direction around the ring.
Now, let's inject our catastrophic failure. Let's say a massive pothole causes a thermal crack or terminal pushout, and the wire completely snaps between house number 3 and house number 4. The bridge is washed out. In an old linear system, houses 4 through 10 are just completely disconnected.
But this is a smart ring. The master board contains a highly advanced microcontroller running a specialized state machine.
A state machine.
Yeah, it's essentially a software program that exists in one specific mode of operation at a time, but can instantly jump to a new mode if triggered by an event.
So what is the trigger here?
The microsecond, the data pulse, fails to arrive at the second port of the master board. The state machine recognizes that the loop is broken. It realizes the mail truck never made it back to the post office.
And how does it react?
It executes what engineers call dynamic self-healing. It takes less time than the blink of an eye. The master board instantly changes its state. Instead of just sending one mail truck out the right side of the lake, it simultaneously dispatches a second mail truck out the left side of the lake.
Wait, it starts reading and writing data from both directions at the same time?
Exactly. The first signal travels down the right side and collects data from houses 1, 2, and 3 until it hits the broken bridge. The second signal travels backward down the left side, collecting data from houses 10, 9, 8, all the way down to house 4, where it hits the other side of the broken bridge.
The wire is physically snapped. The bridge is lying in ruins. But because the master board reached around from the other side, not a single piece of battery data is lost.
The sources confirm this achieves 100% data fault tolerance. And the most incredible part is that this reconfiguration happens so fast that there is absolutely zero torque reduction, no warning lights, and no performance limits imposed on the vehicle.
That is insane.
You could be accelerating hard up a mountain pass, a wire could snap in your battery, the system heals itself dynamically, and you would never feel a single loss of power. The drive remains entirely uninterrupted.
That is software practically performing magic. It completely neutralizes the hardware failure. But wait, eventually the bridge still needs to be repaired, right?
Yeah.
The physical wire is still broken inside the battery pack. When you finally take the car in for a service months later, how does the mechanic even know there is a problem, let alone where to find a single broken wire among thousands?
The genius of the bidirectional ring doesn't stop at just keeping the data flowing. It actually acts as its own diagnostic tool using a feature called the dual test ping.
How does that work?
Think about what the master board is doing. It sent a ping down the right side, and it received responses from slave boards 1, 2, and 3. But it got no response from board 4. Then it sent a ping down the reverse side, and it received responses from boards 10 down to 4, but nothing from board 3.
Oh, it knows exactly where the signal stopped.
Exactly. By analyzing the logic of where the reverse and forward pings terminate, the master board software calculates the exact physical location of the broken wire. It logs a specific subcode in the computer's memory.
So when the mechanic plugs in their scanner, what do they see?
The car doesn't just say internal communication failure. It says the wire harness connecting cell supervisory circuit number 3 to cell supervisory circuit number 4 is physically open.
That is incredible. It turns what used to be a needle in a haystack nightmare for a mechanic, where they would have to manually test hundreds of tiny pins with a multimeter into a precision 5-minute diagnostic check.
It saves countless hours of labor and ensures the exact right part is replaced. But as brilliant as the self-healing ring is, it only solves the problem of a physically broken wire. It doesn't solve the problem of electromagnetic noise.
Right, because the external CAN bus isn't wired in a ring, it's a linear network.
Exactly. So how does the car protect itself when the traction inverter starts screaming its electromagnetic noise, trying to corrupt the ones and zeros?
This brings us to another critical concept from the documents. The ISO 26262 end-to-end, or E2E, protection protocol. I need to define this because ISO 26262 comes up constantly in automotive engineering.
ISO 26262 is the international standard for functional safety in road vehicles. It is a massive, rigorous set of rules dictating how electrical and electronic systems must be designed to prevent unreasonable risks to humans. The E2E protection protocol is a specific software strategy mandated by this standard to ensure data integrity.
Why do we need to protect the integrity of the data? I mean, isn't the data just data?
Not when there is electromagnetic interference present. As we discussed, a massive spike of noise can overpower the tiny voltage differences on the CAN wire. But sometimes it doesn't destroy the whole message.
What does it do then?
It just subtly alters it. It causes what computer scientists call a bit flip.
A bit flip, like turning a digital one into a zero.
Exactly. The data traveling down the wire is just a long string of binary code, ones and zeros. Imagine a packet of data containing the temperature of the battery pack. Let's say the true temperature is 30 degrees Celsius.
Okay.
But as that packet passes by the noisy motor inverter, a single microscopic pulse of electromagnetic energy hits the wire perfectly and flips a critical zero into a 1 in the binary sequence.
So when the data reaches the car's main computer, it doesn't read 30 degrees anymore.
Because of that single flipped bit, the binary number might now translate to, say, 130 degrees Celsius.
The computer thinks the battery is literally on fire.
Yes. The computer receives completely validly formatted data, but the information inside is factually wrong. This is known as ghost data.
And if the computer acts on that dose data?
It might needlessly shut off the car on the highway, causing a massive safety hazard. The E2E protocol is designed to catch these bit flips before the computer can read them.
And how does it catch a flipped bit? It can't know what the temperature was supposed to be?
It uses two brilliant mathematical tools, a rolling counter and a cyclic redundancy check, or CRC. Let's look at the CRC first because it is incredibly clever. Think of the CRC like a complex mathematical wax seal stamped on the outside of every single data envelope.
Okay, a wax seal. How does the math work?
When the battery board wants to send a message, it takes all the ones and zeros inside that specific message, the temperature, the voltage, everything, and runs them through a complex polynomial division algorithm.
It crunches the numbers.
It crunches all those numbers and generates a short, unique mathematical fingerprint, say an 8-bit or 16-bit code.
That's the CRC value, the wax seal.
Yes. It attaches that unique fingerprint to the end of the message and sends it down the noisy wire. Now, the receiving computer at the other end gets the envelope. It doesn't just open it and read the temperature. First, it takes the core message and runs through the exact same polynomial division algorithm itself.
Oh. So it does its own homework to see what the answer should be.
Precisely. If the answer the receiving computer calculates perfectly matches the CRC fingerprint stamped on the envelope, it mathematically proves that not a single bit was flipped in transit. The data is 100% authentic.
But what if our electromagnetic jet engine flipped that bit and changed the temperature to 130 degrees?
Then the underlying data has changed. When the receiving computer runs its math algorithm on the altered data, it will get a completely different answer. It compares its new answer to the original CRC stamp, and they won't match.
The wax seal is broken.
Exactly.
The computer immediately knows the envelope was tampered with by the noise. And what does it do with that ghost data?
It mercilessly and instantly drops it. It deletes the packet from memory and refuses to let the vehicle control unit see it or act on it. It filters out the lies.
That's amazing. And you mentioned a rolling counter, too.
Yeah, the rolling counter adds another layer of security. It numbers every single message sequentially. Message 1, message 2, message 3.
Why number them?
Because electromagnetic noise can sometimes delay a message or cause it to echo. If the computer receives message 5 and then suddenly receives message 3 again, the rolling counter lets it know that message 3 is old, stale data. It drops it.
Ah, I see.
Between the CRC catching flipped bits and the rolling counter catching delayed data, the computer is heavily armored against making decisions based on corrupted information.
It is incredible how resilient the software is. But we have to address the elephant in the room here.
Right.
What happens when the software cannot save the day? What happens if the physical break is so catastrophic, say a piece of road debris slices right through the main CAN bus harness, that no self-healing ring and no mathematical wax seal can fix it? The main computer is truly, totally blind to the state of the high-voltage battery.
That is the ultimate nightmare scenario. When all redundant systems fail, the vehicle must execute its final line of defense to protect human life. This triggers a rigid, heavily regulated protocol known as the fail-safe and the FTTI response.
FTTI, fault-tolerant time interval. Let's dig into the sequence of events here, because the timing of this protocol is absolutely fascinating.
When the communication data stops arriving, the main computer does not panic instantly. If you lose Wi-Fi in your phone for a split second, you don't instantly throw the phone away,
Oh,
right?
you wait a second for it to reconnect.
Exactly. The car's computer does the same thing. It initiates a debounce window of exactly 500 milliseconds.
Half a second.
Yes. For half a second, the car holds its breath. It continues driving normally, using the very last known good data it received, waiting to see if this is just a passing glitch or a massive electromagnetic surge that will clear up.
But if 501 milliseconds pass, and there is still no data,
Then the system declares a critical emergency. The debounce window closes and the FTTI timer begins. By international safety law, the vehicle's control software has exactly 2 seconds from the start of the fault to bring the entire moving vehicle into a predetermined safe state.
2 seconds. That is almost no time at all. What can the car possibly do in 2 seconds while traveling at 70 miles an hour?
It executes a highly orchestrated choreography between the battery management system and the vehicle control unit, the VCU. Step 1 happens instantly. The VCU cuts the available motor power by 50%. It limits the acceleration. If you are plugged into a charger, it instantly aborts fast charging.
Okay, so it slows things down.
But step 2 is the most critical part. It executes a soft cutoff of the high voltage system.
A soft cutoff. Why so? If the car is in a critical emergency, why not just flip the master emergency switch and disconnect the battery instantly? A hard cutoff.
Because a hard cutoff under heavy load would be incredibly dangerous, arguably more dangerous than the communication loss itself.
Really? Why?
Think about it. You are driving 70 miles an hour. The electric motors are actively pulling hundreds of amps of current from the battery to maintain that speed.
Right. It's a massive river of electricity flowing through the physical high-voltage contactors, the main relays connecting the battery to the car.
Exactly. If you send a command to violently rip those physical metal contactors open while hundreds of amps are actively flowing through them, the electricity doesn't just stop. It has momentum. It will physically jump the air gap between the separating metal plates.
It creates a spark.
It creates a gigantic, highly destructive electrical arc. It's essentially a sustained lightning bolt inside the contactor housing. That arc is thousands of degrees hot. It can melt the metal contacts, welding them permanently shut, or worse, the immense heat can ignite the surrounding plastics and cause a catastrophic battery fire right under the passenger cabin.
Wow. So you cannot just pull the plug on a heavy electrical load.
Never. So instead of a hard cutoff, the software must orchestrate a graceful shutdown in a fraction of a second. The VCU sends an immediate command to the motor inverters. Drop your torque demand to absolute zero.
It tells the motors to stop pulling current first.
Exactly. In milliseconds, the inverter stops chopping the power, and the massive river of current slows to a trickle and then hits 0 amps. Only then, once the current is verified to be near zero, does the system send the command to physically open the high-voltage relays.
And because there is no current flowing, the metal plates separate smoothly. No arc, no fire, no damage.
The high-voltage system is safely isolated. The car glides into a physical state of zero propulsion power, allowing the driver to maintain steering and braking control to safely navigate to the shoulder of the road.
All in 2 seconds.
Right. This entire complex sequence, diagnosing the fault, waiting the 500 milliseconds, demanding zero torque, and safely opening the physical relays, must be executed perfectly within that 2.0-second FTTI window.
It is a stunning piece of systemic engineering. The software essentially catches the failure midair and cushions the fall so the driver isn't hurt. But I have to bring us back to reality here.
Okay.
While bidirectional self-healing rings and mathematically perfect soft cutoffs are brilliant, isn't this all just a highly advanced Band-Aid? If we know these wires break from vibration and heat, shouldn't the engineers just figure out how to make the hardware survive the environment in the first place?
You have hit on the exact tension that exists in every automotive engineering department in the world. Software mitigation is the safety net, but you do not want to fall into the safety net if you can avoid it. You want to build a better bridge.
Exactly.
And that brings us out of the realm of software architecture and into the physical design offices. We are entering the world of DFMEA.
DFMEA. Let's define this for everyone. Design failure mode and effects analysis. From my understanding, this is essentially an extremely formal, highly structured brainstorming session where engineers sit around and try to imagine every conceivable way their product could spectacularly fail.
It is institutionalized, structured paranoia. They look at every single component and assign it a severity score, an occurrence score, and a detection score. According to our specific documents, a total communication blind spot on the CAN network is given a severity score of 8 out of 10.
An 8 out of 10. That means a failure doesn't just trigger an annoying warning light. It fundamentally degrades the primary function of the vehicle and likely leaves the user stranded on the side of the road waiting for a tow truck.
Exactly. Because it is an S.8, the DFMEA mandates that engineers must implement aggressive physical design changes to harden the hardware against those root causes we discussed earlier. Let's look at how they tackle the EOS, the high-voltage surges that punch through the isolation barriers.
Right, the floodgates. How do you build a stronger floodgate on a microscopic circuit board?
The designers specify the use of automotive-grade electromagnetic isolation chips that are physically rated to withstand greater than 3,000 VRMs. That's volts root mean square.
3,000 volts. That seems like a massive overspecification for a battery pack that only operates at 400 or 800 volts.
In electrical engineering, especially safety-critical systems, massive overspecification is the entire point. You aren't designing for the steady 800 volts. You are designing for the fraction of a second, a transient spike that happens when a contactor arcs or a lightning strike induces a surge nearby.
Better safe than sorry.
Exactly. But even 3,000-volt isolation isn't enough to satisfy the DFMEA. They also mandate the use of high-impedance common mode chokes, or CMCs, physically soldered onto the communication lines.
Okay, let's break down a common mode choke. What does it actually look like, and how does it protect the data?
If you look at a circuit board, a CMC looks like a tiny black cube or a tiny donut made of ferrite, which is a magnetic ceramic material. Inside that tiny donut, the two copper wires of the CAN bus are tightly wound around the ferrite core.
So the data wires actually pass right through this magnetic donut. What does that achieve?
It utilizes the physics of electromagnetism to filter out the noise. Remember how the CN bus uses differential signals? One wire goes positive, the other goes negative.
Right.
Because the currents are flowing in opposite directions through the wires wrapped around the donut, the magnetic fields they generate completely cancel each other out. To the differential data signal, the choke is invisible. The data flows right through without slowing down.
But what about the electromagnetic noise from the motor inverter? The jet engine noise?
That noise is common mode. The massive electromagnetic shock wave washes over both wires in the exact same direction at the exact same time. When those two parallel spikes of current hit the coils inside the ferrite donut, their magnetic fields don't cancel out, they add together.
They multiply.
Yes. And the ferrite core reacts to that massive combined magnetic field by instantly generating a massive electrical resistance, a high impedance, specifically against that noise.
So it blocked it.
It literally chokes out the interference, absorbing the energy as a tiny bit of heat while letting the clean differential data pass through untouched.
It is a physical magnetic bouncer at the door of the microchip, only letting the right kind of electricity inside. That is brilliant. And the documents also mention TVS diodes for handling hot plugging.
TVS stands for transient voltage suppression. Think of these diodes as electrical shock absorbers. Hot plugging occurs when a mechanic unplugs or plugs in a live connector, or when a relay slams shut. It creates a sudden, sharp voltage spike.
Okay, and the diode stops that.
The TVS diode sits quietly on the circuit board, invisible during normal operation. But the millisecond the voltage spikes dangerously high, the diode's internal resistance collapses. It instantly clamps down, short-circuiting the kilovolt level surge harmlessly to the ground plane.
Completely bypassing the delicate microchips behind
Yeah,
it. Okay, so that hardens the physical chips against raw electrical violence. But what about the CAN bus going bus off? We talked about how the error counter hits 255 because of a standing wave, and the computer just shuts itself down to protect the car. How does the DFMEA design the system to recover from a software shutdown?
They implement a highly specific recovery algorithm governed by the AUTOSAR standard, known as CAN-SM, or CAN State Manager. It is a bus-off adaptive recovery algorithm.
Okay, adaptive recovery.
The engineers recognize that not all noise is permanent. Sometimes a massive burst of interference is just passing by. Maybe you drove perfectly parallel to a high-powered military radar station or a massive industrial power line.
Right, a temporary environmental hazard.
Right. If the CAN bus shuts off because of a temporary hazard, it would be foolish to leave the driver stranded on the highway. So the software doesn't just give up. It actively tries to fight its way back online using a two-stage process.
Stage 1 is quick recovery. How quick are we talking?
The exact moment the CAN controller goes bus off, the software starts a timer for exactly 50 milliseconds.
That is barely enough time to blink.
It is just enough time for a transient spark or a burst of radio interference to dissipate. After 50 milliseconds, the software forcefully resets the CAN controller, wipes the error counters back to 0, and attempts to reconnect to the network.
And if the interference is gone, the car is instantly back to normal. The driver probably never even knew communication was lost.
Exactly. But what if the interference isn't a passing radar station? What if a physical wire harness has rubbed through its plastic insulation because it was routed against a sharp metal bracket, and the bare copper wire is now physically short-circuiting directly against the car's metal chassis?
That is a hard, permanent fault.
Yes, in that scenario, when the quick recovery forcefully reconnects after 50 milliseconds, the data immediately hits the short circuit. The error counters instantly hit 255 again, and the system crashes back into bus off within microseconds.
So it tries again.
It will try this rapid 50-millisecond quick recovery loop up to 5 times in rapid succession. If it fails all 5 times, the software's logic concludes that the problem is not a temporary phantom, it is a severe physical reality.
Okay.
And so it shifts into the second stage, slow recovery.
And what does slow recovery do?
It drastically slows down the retry attempts. Instead of trying every 50 milliseconds, it waits a full 2,000 milliseconds, 2 entire seconds, before attempting to reconnect again.
Okay, let me pause you right here. I need to push back on this logic. Think about this from the perspective of someone sitting in the driver's seat. If I lose connection to the battery powering my vehicle on a busy interstate, I want that connection back instantly.
I understand that instinct.
If the computer knows there's a problem, why on earth is it programmed to give up and sit on its hands for 2 full seconds between attempts? In computer processing time, 2 seconds is an absolute eternity. Why not just keep rapid-firing retries every 50 milliseconds forever until something shakes loose and it works?
It is a perfectly logical question, but it ignores the physical reality of the hardware. The answer comes down to thermal limits and resource management. Let's look at the hardware first. When a CAN transceiver chip tries to transmit a strong digital signal into a dead short circuit like a wire touching the chassis, it essentially dumps its maximum output current directly into a wall.
It is straining as hard as it can.
And pushing maximum electrical current generates heat. If you force that chip to rapidly retry every 50 milliseconds indefinitely, the silicon inside the transceiver cannot dissipate the heat fast enough.
It overheats.
The temperature will spike exponentially, and within seconds, you will literally melt the transceiver chip right off the circuit board. You will turn a temporary short circuit into a permanent hardware destruction.
Oh, so by waiting 2 seconds, you're giving the physical chip time to cool back down to a safe temperature before straining it again.
Exactly. It is hardware self-preservation. But there is a second, equally important reason. The act of resetting the CAN controller, flushing the memory buffers, and attempting to reestablish network handshakes takes a significant amount of the main CPU's processing bandwidth.
The computer's attention is focused on fixing the broken network.
Right. And the main CPU has other things to do. It needs to manage the anti-lock brakes, it needs to monitor the steering angle, it needs to deploy the airbags if necessary. If you consume 90% of the CPU's processing power trapped in an infinite loop trying to fix a broken battery wire, the computer might lag or fail to execute a critical braking maneuver.
Ah, so the 2-second wait is to let the CPU breathe, to ensure the rest of the car remains safe and functional while it periodically checks to see if the battery network has miraculously healed itself. That actually makes perfect sense when you explain the physics of it.
It is a delicate balancing act engineered into the DFMEA. Now, the final design strategy we need to discuss from the source material is entirely physical. It is called spatial routing boundaries.
The actual architectural blueprint of where the physical wires snake through the car's chassis.
Precisely. We know the high-voltage cables carrying power to the motors are radiating massive magnetic fields. You cannot stop that. So the engineers mandate that the low-voltage communication wires must be heavily armored. They mandate the use of twisted pair-shielded cables.
Okay, shielding makes sense. Wrapping the wire in a metal foil to block the noise. But why twist the wires?
Twisting the wires is one of the oldest and most effective tricks in electrical engineering, going all the way back to Alexander Graham Bell and the first telephone lines. When you twist the two CAN bus wires around each other, you ensure that any external magnetic interference hits both wires equally.
Which keeps the interference common mode.
Right, allowing those common mode chokes we discussed earlier to filter it out perfectly. But more importantly, the twisting physically alternates the position of the wires, which causes the tiny magnetic fields generated by the wires themselves to cancel each other out. It keeps the noise out, and it keeps the signal clean.
But even with twisted wires and metal shielding, the DFMEA goes a step further, doesn't it?
It does. The blueprint strictly prohibits routing these sensitive communication harnesses anywhere near the high-voltage bus bars. They mandate a strict minimum physical separation distance.
That's our part.
The low-voltage and high-voltage lines must be greater than 100 millimeters apart at all points in the vehicle.
Because even with the best shielding in the world, the magnetic fields generated by a cable pulling hundreds of amps at full throttle are just too violent. You have to physically quarantine the data lines.
Distance is the ultimate unbreakable shield against electromagnetic coupling. The magnetic field strength drops exponentially with distance. By enforcing that 100 millimeter boundary, they guarantee the noise never reaches the wires in the first place.
Okay, so we have this perfect blueprint. The DFMEA is absolutely flawless. We have mathematically precise twisted wires, 3,000-volt isolation barriers, magnetic bouncers, adaptive thermal cooling software, and a strict physical quarantine. The design is a masterpiece.
On paper, yes.
Right, on paper. But here is the massive reality check. You can design the most perfect architectural blueprint on a computer screen in a quiet, air-conditioned office in Germany or California, but it means absolutely nothing if the factory builds it wrong. How do automotive companies guarantee that these hyper-strict microscopic rules are actually followed on a massive, loud, messy, high-speed assembly line by hundreds of different human workers?
And that profound transition leads us directly into part 4 of our deep dive, the PFMEA, the process failure mode and effects analysis. We have left the design office, and we are now standing on the factory floor looking at how to build the unbreakable.
The sources outline a methodology here called 5M1E. Let's establish what that means.
5M1E is a fundamental framework in manufacturing quality control. It stands for man, machine, material, method, measurement, and environment. When engineers analyze the factory floor, they look at how every single one of those 6 variables could introduce an error into the assembly of our communication network.
And the primary weapon they use to enforce perfection across those variables is a Japanese manufacturing philosophy called poka-yoke. I love this concept.
Poka-yoke translates to mistake-proofing or inadvertent error prevention. The philosophy is simple. You do not rely on a worker to remember a rule or to try their best. Humans get tired, they get distracted, they make mistakes.
So what do?
Instead, you design the physical manufacturing process so that it is physically, literally impossible for the worker to do the task incorrectly.
Let's apply that to the physical wire routing we just talked about.
Yeah.
The DFMEA rule was a strict 100 millimeter separation between the high voltage cables and the low voltage CAN wires. How do you poka-yoke that on a chaotic assembly line?
Yeah.
You can't just hand a worker a ruler and tell them to measure it every time.
Exactly. You don't use rulers. The engineers designed the massive plastic battery casing with highly specific geometry constraints. They mold intricate physical routing channels directly into the plastic.
Okay, pre-made paths.
And the low-voltage wire harness is designed so that it physically cannot reach the high-voltage area. The wire is simply cut too short to stretch that far.
So even if the worker wanted to route it wrong, the wire physically wouldn't let them.
Right. Furthermore, they use specific, brightly colored fire-retardant sleeves and corrugated plastic tubes that encase the wires. These tubes have uniquely shaped plastic clips pre-attached to them.
Let me guess. The clips only fit in specific holes.
Exactly. And those clips only snap into specifically shaped, color-coded receiving holes on the battery chassis. A square peg cannot physically go into a round hole.
It is 100% prevented by the physical geometry of the parts. That is brilliant. What about the twist pitch of the communication cables? We talked about how vital it is that the wires are twisted.
The PFMEA strictly controls the twist pitch, the distance of one complete twist of the 2 wires. The specification demands it must be tightly controlled between 20 millimeters and 30 millimeters.
I picture this exactly like braiding a heavy rope to use on a boat. If you braid the fibers tightly and evenly, the rope is incredibly strong and keeps the water out. But if the person braiding it gets lazy and the braid's too loose, say the twists are 50 millimeters apart, the structure weakens and the weather gets inside. In this case, the weather is electromagnetic noise slipping through the gaps in the loose twist and destroying the signal.
That is a perfect analogy, because the tightness of the twist dictates the exact frequencies of noise that are blocked. Deviation is unacceptable. So, Poka-yoke dictates that humans do not twist the wires. Automated twisting machines do it.
I was going to say, a human can't measure 20 millimeters by hand all day.
No way.
No.
And they don't just trust the machine either. They have optical laser sensors continuously scanning the wire as it spools out, visually measuring the twist pitch in real time to ensure it never deviates from that 20 to 30 millimeter window. If it hits 31 millimeters, the machine instantly stops and flags an error.
Unbelievable precision. Okay, moving down the list of vulnerabilities we established earlier, what about those little connector pins wiggling loose over potholes? The fretting and the terminal pushout? How does the factory guarantee those pins are locked in forever?
They attack this from two angles: the assembly of the connector and the assembly of the wire itself. Let's look at the connector first. They use plastic housings engineered with TPA and CPA double locks.
Terminal position assurance and connector position assurance.
Yes. When the worker inserts the metal pin into the plastic housing, it clicks. But a click isn't enough. The worker must then slide a secondary, brightly colored piece of plastic, the TPA, perpendicularly across the back of the connector.
What does that do?
This piece of plastic physically slides behind the metal pin, physically barring it from ever moving backward, even under massive vibration.
A double lock. But how do you know the worker actually crimped the wire onto the tiny metal pin correctly in the first place? If the crimp is weak, the wire just pulls out of the pin.
This is where the machine and measurement parts of 5M1E shine. The crimping is done by heavy pneumatic presses on the assembly line, but the molds inside the press feature 100% dynamic pull force monitoring.
Wait, so the machine that crushes the metal onto the wire actually tests how strong its own crush is in real time?
Every single time it stamps a pin, internal force sensors and displacement lasers measure the exact pressure curve of the metal deforming around the copper wire. It compares that microscopic pressure curve against a mathematically perfect digital model.
And if it doesn't match?
If the pressure is even slightly too soft, meaning the crimp is loose, or too hard, meaning the copper wire was damaged, the machine instantly rejects the part into a scrap bin before the worker can even touch it.
It guarantees a mechanically perfect bond every single time.
And they apply that same level of microscopic paranoia to the circuit boards themselves. You remember the thermal cracking we discussed? The microscopic solder joints holding the heavy ceramic components failing?
Yes, the SMT, surface mount technology components.
You cannot rely on human eyes to inspect thousands of microscopic silver dots moving by on a conveyor belt. So the factory employs multi-stage optical and radiographic inspection.
Like cameras.
Exactly. Every single board goes through 3D AOI, automated optical inspection, and SPI, solder paste inspection. Laser scanners map the exact volume and height of the solder paste applied before baking.
And after baking.
They pass the boards through 3D X-ray screening machines.
They're literally taking X-rays of the computer chips.
They have to. The X-ray looks straight through the solid components to inspect the hidden solder joints underneath. It algorithmically hunts for tiny voids, bubbles, or microcracks inside the solid metal of the joint that are completely invisible to the naked eye. If the X-ray sees a bubble, the board is scrapped.
Okay, this is starting to feel less like a car factory and more like a semiconductor clean room or a sci-fi movie.
It gets even more strict. The sources detail the environmental controls over the SMT line. They specifically mandate strapping dynamic ESD electrostatic discharge grounding monitors directly to the bodies of the human workers.
Because of static shock. The human body generates static electricity just by existing and moving. You shuffle across a carpet, you touch a metal doorknob, you get a painful shock.
That shock you feel is thousands of volts of static electricity discharging in an instant. Now, imagine a factory worker simply shifting their weight in their chair, building up a tiny static charge, and then picking up a delicate CAN transceiver chip to place it in a machine.
The static electricity jumps from their finger into the chip.
And because the microscopic silicon traces inside that chip are only designed to handle 3 volts, that tiny invisible static discharge acts like a lightning strike. It completely fries the internal logic gates.
But the worst part is, it might not completely destroy the chip right away, right?
Exactly. It creates a latent defect, a microscopic burn mark inside the silicon that passes initial quality checks but will inevitably fail 3 years later when the customer is driving down the highway.
So how do they stop that?
To prevent this, the workers wear conductive wrist straps physically tethered to grounding wires. And the dynamic monitors constantly measure the electrical resistance of the worker's skin to ensure the grounding path is perfect.
And if they take the strap off?
If the grounding wire snaps or is removed, an alarm sounds instantly and the line stops. The worker physically cannot zap the chips.
Unbelievable. And while we are talking about the factory environment, the documents highlight the TCT, the temperature curve of the reflow ovens.
Yes. When the circuit boards are assembled, they pass through a massive long oven to melt the solder paste and permanently attach all the components. This is the reflow oven. But you can't just blast the board with maximum heat.
Because of the thermal shock, the CTE mismatch we talked about in the very beginning.
Exactly. If you heat the board too quickly, the fiberglass expands violently while the rigid ceramic component stays stiff, and you induce microstress cracking in the components before the car is even built.
So they have to heat it slowly.
Very specifically, manufacturing engineers spend weeks heavily optimizing the temperature curve, the TCT. They meticulously program the exact ramp-up speed in degrees per second, the exact peak temperature, and the exact gentle cool-down speed to ensure perfect solder flow with absolute zero thermal stress introduced into the ceramics.
Which brings us to the final test on the factory floor. Speaking of perfect components, we have to talk about those 120 ohm terminal resistors. The tiny parts that prevent the bathtub standing waves. The entire network collapses if one is missing. How do they know, with absolute 100% mathematical certainty, that both of those resistors are perfectly attached before they bolt the heavy steel lid onto the battery pack and seal it shut forever?
This is, in my opinion, one of the most elegant and satisfying tests on the entire assembly line. It is part of the EOL, or end-of-line, testing. Before the lid goes on, an automated diagnostic tester plugs directly into the CAN bus port of the battery.
Okay, what does it do?
The first thing it does is send a tiny, precise amount of direct current down the lines to measure the total DC impedance, the electrical resistance of the entire closed network.
Okay, let's do the math on this because it's a beautiful proof. We have a long wire. We have 120 ohm resistor soldered at the far left end. We have a second 120 ohm resistor soldered at the far right end.
And basic electrical physics dictates that when you have two resistors of equal value wired across the same two lines, wired in parallel, the total resistance of the entire circuit is exactly half the value of one resistor. So 120 divided by 2 is 60.
Therefore, the test machine must read exactly 60 ohms.
The factory specification demands the reading must fall exactly between 59 and 61 ohms.
What happens if the machine reads 120 ohms?
If the reading is 120 ohms, it mathematically proves that only one resistor is active on the network. The other one either fell off, was never placed by the machine, or has a cracked solder joint. The math exposes the physical flaw instantly.
What if it reads, say, 10 ohms or 0 ohms?
Then you have a massive short circuit somewhere deep in the wiring harness. Wires are touching that shouldn't be. The stripped 59 to 61 ohm window is a binary, mathematically perfect proof of the physical integrity of the entire network.
It's like a pass-fail grade for the physical wiring.
Exactly. If it passes that single test, the engineers know the physical structure is fundamentally sound. They also inject high levels of artificial interference into the line at this stage to test the bit error rate, proving the communication chips can actively filter noise before the battery is cleared to leave the factory.
The level of paranoia, the sheer volume of checks and balances, it is staggering. But as our source documents make very clear, even after the battery pack leaves the clean, perfect environment of the factory floor, carrying its mathematical stamp of approval, it still has to prove it can survive the real world.
Because the real world is infinitely more chaotic than a factory. And that brings us to the final, and honestly, the most brutal stage of our deep dive.
We are entering Part 5, the DVP&R, the Design Verification Plan and Report. I like to call this the ultimate torture test.
That is a very accurate description. This is the validation phase. This is where automotive engineers must definitively prove that all of the brilliant software designs and all of the paranoid factory manufacturing controls we just discussed will actually survive a mandatory 10-year, 300,000-kilometer life cycle in the hands of everyday drivers.
And they don't prove this by just driving the car nicely around a sunny test track in California, do they?
Not at all. They subject the components and the entire vehicle to absolute physical and digital torture in highly controlled laboratory environments. Let's look at the validation for that bidirectional ring topology first, the self-healing mail truck route.
The ISO-SPI ring fault injection. How do you test a broken wire without actually destroying a new battery pack?
They use a massive computing rig called a hardware-in-the-loop, or HIL, simulator. They take the actual physical master board and all the slave boards and hook them up to a supercomputer that mathematically simulates the electrical behavior of thousands of battery cells in real time.
Wow.
The system believes it is driving down a highway, pulling data from all the cells.
The brain is hooked up to the matrix.
Exactly. And while the system is happily communicating, the engineers use physical fault injection hardware to literally snap the digital connection between two specific slave boards, say LMU3 and LMU4. They artificially sever the spinal cord while the system is under full load.
And what are the pass criteria for this test? How fast does the software have to react to pass validation?
The standard is incredibly strict. The master board's state machine must recognize the break, trigger the dynamic self-healing, and completely reroute the data flow from the reverse direction within 50 microseconds.
50 microseconds. That is a fraction of a millisecond. That is less time than it takes a camera flash to go off.
And during that unimaginably brief transition window, the pass criteria dictate that it must drop exactly 0 cell data frames. It must trigger exactly 0 warning alarms on the simulated dashboard. And it must command exactly 0 power deshrating to the motors.
0 margin for error.
If even one single bit of data is lost, or if the driver would feel even the slightest hesitation in the pedal, the system fails the entire validation.
That proves the software immune system is flawless. But what about testing against our main villain, the electromagnetic noise from the traction inverter, the roaring jet engine? How do they test that in a lab?
They conduct full vehicle EMI, electromagnetic interference, torture tests. They take a fully built prototype vehicle and strap it down onto a chassis dynamometer inside an anechoic chamber, which is a massive room lined with metallic foam spikes that absorb all radio waves.
A chassis dyno is essentially a giant, heavy treadmill for cars, right? The wheels spin, but the car stays still.
Yes. They run the car on the dyno at maximum violent acceleration, taking the motors to their red line, and then immediately slam the system into maximum regenerative braking. They repeat this cycle constantly,
Generating as much noise as possible.
Exactly. This forces the silicon carbide switches in the inverter to generate the absolute maximum possible electromagnetic noise. The car is physically screaming with interference.
The engineers are paranoid, so that's not enough noise, is it?
No, they want to push the communication lines past the breaking point. While the car is screaming on the dyno, the engineers take specialized signal generators and directly inject an additional 1.5 volts of high-frequency electrical noise oscillating between 10 kilohertz and 20 kilohertz directly onto the physical surface of the CAN bus wires.
They are actively conducting electronic warfare against their own vehicle. They are actively trying to jam the signal.
They are throwing everything they can at those common mode chokes and twisted wires to see if they break, and they run this combined torture test continuously for 24 hours straight.
24 hours of maximum interference.
Yeah.
What is the pass criteria for the data integrity?
The error frame rate on the CAN bus must be exactly 0.0%, not 1%, not 0.1%, absolute zero. Over 24 hours of maximum dynamic load and active electronic jamming, the physical twisting of the wires, the magnetic bouncers, and the mathematical CRC wax seals must perfectly protect every single one of the billions of data bits transmitting across the network.
That is just staggering confidence in their engineering. Okay, now let's talk about the final 2 tests, which deal with power collapse. The 12-volt brownout test, and my absolute favorite name in the entire engineering document, the babbling idiot test.
The brownout test validates the hardware's resilience against the rest of the car failing. They simulate a failing, dying 12-volt battery by suddenly dropping the power supply to the communication transceivers down to a measly 4.5 volts for a grueling 50 milliseconds.
We established earlier that at 4.5 volts, the silicon chips lock up. So how do they survive?
The engineers designed tiny backup capacitors directly onto the circuit board next to the chips. Think of them as tiny emergency water towers.
Okay, I like that.
When the main power drops to 4.5 volts, these microscopic capacitors instantly discharge their stored energy, keeping the chips artificially awake and fully functional for that 50 millisecond window, completely preventing the computer from resetting or rebooting.
Like holding your breath underwater as a wave crashes over you. You come up the other side completely fine.
Exactly. But the babbling idiot test is the real star of the software validation. It tests the absolute worst-case scenario on the CAN network.
The sources describe this test as flooding the bus with 95% high-priority junk data. Can you explain the setup?
In a CAN network, messages are prioritized by their ID number. The lower the ID number, the higher the priority. ID 0x00 and 0E001 have the absolute right-of-way. Every other computer must stop talking and listen when a message with that ID is sent.
So it's like a VIP pass.
Right. In the babbling idiot test, the engineers take a simulator tool and forcefully inject messages with those top priority IDs continuously, taking up 95% of the entire physical bandwidth of the wire with total meaningless garbage data.
Okay, I have to step in and ask about the reality of this. Is this just engineers being intentionally cruel for the sake of an impossible test? Is it really likely or even possible that a car's internal network would suddenly start aggressively spamming itself with 95% junk data while you were driving?
It is a highly realistic scenario, and it is the reason this test exists. Let's look at the real world. A modern EV has dozens of minor sensors tapped into the CAN bus. Say you have a simple, cheap ambient temperature sensor located behind the front bumper.
Okay.
Now imagine you drive through a massive, deep puddle during a rainstorm. Water forcefully intrudes into the cheap plastic connector of that sensor and shorts out its internal microcontroller.
The water fries the cheap chip.
But it doesn't just kill it, it severely damages the logic gates. That broken waterlogged chip might suddenly go completely crazy and start transmitting its temperature data continuously, millions of times a second, accidentally using a high-priority ID.
Oh, it's not a malicious hacker. It's a broken, babbling component on the network that physically cannot stop talking.
Exactly. It becomes a babbling idiot. And because it is using a high-priority ID and shouting constantly, it physically hogs the entire copper wire. The critical safety messages, like the high-voltage battery warning the car that it is overheating or the brake pedal telling the motor to slow down, cannot get through the noise. They are blocked.
That is terrifying. The car is effectively paralyzed by a broken bumper sensor. So how does the battery management system pass this impossible test? It can't stop the sensor from babbling.
It cannot. But it can save the car. The BMS must recognize that it is being blocked from communicating with the vehicle control unit. It must successfully diagnose the U0100 or U0111 communication failure within exactly 1.0 seconds of the attack starting.
Okay, 1 second to diagnose.
And then it must trigger the FTTI rigid response we discussed earlier. It has exactly 2.0 seconds total to bring the vehicle into the safe state.
The 50% power cut, the soft cutoff of the contactors, the limpo mode?
Yes. It successfully identifies that the network is under a denial-of-service attack from its own sensor, protects the high-voltage system from acting unpredictably, and gently limits propulsion power so the driver can safely pull over to the shoulder, all while totally blinded by the babbling data.
It essentially realizes it is going blind and immediately pulls the emergency brake safely. That is incredible. The final piece of the validation mentioned in the sources wraps all of this physical and digital testing up with some heavy statistical and visual proofs before mass production begins. They verified the twist pitch of the factory machines using statistical process control, or SPC.
This is pure mathematics validating the factory floor. They measure thousands of wire twists and calculate a process capability index, or CPK. The standard requires a CPK of 1.67 or greater.
What does a 1.67 actually translate to in the real world?
It means the automated factory process is so incredibly tight, so perfectly controlled, that the statistical defect rate is less than 1 error in every million parts produced. It is near perfection.
But the visual test they do, the final validation called the eye diagram test, really caught my attention as a perfect summary of everything we've talked about. Can you explain what an eye diagram actually is?
The eye diagram is one of the most beautiful pieces of engineering visualization in existence. Imagine you hook an advanced oscilloscope up to the CAN bus wires. You are watching the voltage rise and fall as millions of ones and zeros fly by. Normally, it just looks like a solid blur of green light on a screen.
Because it's happening millions of times a second.
Right. But an eye diagram software tool takes every single one of those millions of high-to-low and low-to-high voltage transitions and perfectly overlays them on top of each other on the screen, synchronized to the timing clock.
So it grooves all the shapes together.
Yes. And if the signal is perfectly clear, the transitions from high to low create a wide open hexagonal space right in the middle of the screen where no voltage lines cross. It visually looks exactly like a wide open human eye.
A wide open eye means perfect clarity.
It proves that the voltage levels are strong and distinct. There is absolutely no signal reflection or standing waves muddying the waters, and the physical timing of the bits is flawless. The factory EOL validation requires the mathematical area of that eye diagram to be greater than or equal to 80% open.
And what happens if there is interference? Say, the twist pitch was too loose, or one of those 120 ohm resistors was cracked and caused a standing wave.
The bouncing waves and the electromagnetic noise cause the voltage transitions to become sloppy and poorly timed. The glowing lines on the oscilloscope start to bleed into the center of the hexagon. The visual eye closes.
And a closed eye means fatal interference.
A closed eye means the main computer can no longer clearly distinguish a 1 from a 0. This visual proof of an open eye, combined with a strict bit error rate requirement of less than or equal to 10 to the negative ninth power, which is the ultimate ASIL automotive safety integrity level standard, guarantees the absolute integrity of the physical and digital system before the vehicle ever reaches a customer's driveway.
So what does this all mean? Let's take a step back and recap this unbelievable journey through the hidden nervous system of an EV. We started by looking at the microscopic chaos of the real world. The physical violence of thermal expansion slowly cracking tiny solder joints holding ceramic chips. Low-voltage metal pins vibrating against each other until they literally microarc and rust themselves into insulators.
Right.
And massive kilovolt surges from fast chargers punching literal holes through electrical isolation floodgates.
We saw the immense physical vulnerabilities of placing a delicate computer network inside an incredibly harsh mobile environment.
And then we explored the invisible threats. The high-frequency magnetic shock waves roaring from the motor inverter, trying to drown out the digital whispers.
Yeah.
And tiny 120 ohm resistors falling off, removing the sandy beach and turning the electrical wires into chaotic, wave-reflecting bathtubs that crash the entire network.
But then we saw how the engineering world fights back. We saw the digital immune system. The bidirectional self-healing rings that sense a broken wire and instantly send data backward around the loop, achieving 100% fault tolerance in 50 microseconds.
It's just so fast.
The rolling counters and complex mathematical CRC wax seals that identify and mercilessly drop corrupted coast data, and the rigid, highly choreographed 2-second failsafe that demands zero torque to execute a soft cutoff, safely opening high-voltage relays without a massive, fiery spark if all else truly fails.
We explored the structured paranoia of the design phase, mandating 3,000-volt isolation barriers, magnetic ferrite bouncers to choke out noise, and adaptive recovery software that forcefully waits 2 whole seconds so it doesn't melt its own silicon chips. We walked to the factory floor, seeing mistake-proof physical connectors, deeply monitored crimping machines, workers tethered to grounding wires, X-ray machines hunting for invisible bubbles, and the pure mathematical beauty of the 59 to 61 ohm end-of-line test.
And finally, we witnessed the torture. Artificial wire cuts while simulating highway speeds, 24 hours of active electronic noise warfare on a screaming chassis dyno, and babbling idiot denial of service attacks from flooded sensors, all to statistically prove the system can survive its 10-year life cycle.
And the most profound part of all of this is that every single thing we just discussed happens completely invisibly. It all happens beneath the floorboards in fractions of a millisecond so that your drive remains completely uninterrupted, completely boring, and completely safe. So you, listening to this right now, the next time you hit a massive pothole that rattles your teeth, or the next time you plug your car into an ultra-fast DC charger and hear those giant mechanical contactors cluck shut beneath your feet, just remember, there's an entire staggering symphony of microsecond state machine checks, perfectly twisted shielding, 59 ohm resistance validations, and error frame corrections happening in the dark right below you, entirely dedicated to keeping you safely moving forward.
It really is one of the great unseen marvels of modern technology. But, it does raise one final crucial thought for you to mull over after this deep dive ends.
Oh, what's that?
We have just spent an entire hour detailing the millions of dollars of research, development, and factory precision required to perfectly protect, twist, shield, and digitally heal these physical copper wires and connectors.
It is a monumental effort just to keep a simple wire doing its job.
It is. But the cutting edge of the automotive industry, the very next generation of electric vehicles currently in development, is rapidly moving toward a completely new architecture. The wireless BMS.
Wireless, as in inside the sealed battery vault.
Yes. Engineers are looking to remove the internal copper communication wires entirely. The goal is to save significant weight, free up physical space for more battery cells to increase range, and completely eliminate the massive manufacturing complexity and expense of routing those physical wiring harnesses.
Well, I suppose that instantly solves the physical breaking problem, right? You cannot snap a wire if it doesn't exist. There is no more fretting, no more thermal cracking of joints holding cables, no more terminal push-out.
That is the compelling argument. But think deeply about everything we just discussed regarding the invisible threats. If we completely remove the twisted pairs, if we remove the thick metallic shielding, how will the next generation of engineers protect the battery's incredibly sensitive nervous system when all of that critical safety data is just floating completely exposed through the air?
Oh,
It will be entirely vulnerable to the massive electromagnetic shock waves of the traction motor, exposed to entirely new forms of environmental signal jamming, and for the first time, potentially vulnerable to direct wireless cybersecurity threats from the outside world.
wow. We just spent an hour learning exactly how engineers built the perfect armor for the digital spinal cord. And the next step in human progress is to throw away the cord entirely and rely on digital telepathy in the middle of a war zone. That is a truly wild thought to leave on. Thank you so much for joining us on this deep dive. Keep questioning the hidden technology in your everyday life. Stay curious, and the next time you are cruising down the highway doing 70, well, just be incredibly thankful that your car's brain and its muscles are having a very clear, very well-protected conversation.